as said before, the question will be in between 3:30 to 4 p.m. So let's welcome Chip again.
Do I need to completely power down to get back up on? Did I, or do you want me to? All right, so I'll start back up again. So one of the materials that is relatively new on the horizon is something that is known as compost tea. Are any of you familiar with compost tea as a material or have any understanding of it? Okay, so some. So compost tea is simply a high quality extract of all of the beneficial microbial life that exists in compost. So if we identify that compost gives us multiple things, including nutrient, organic matter, and microbial life, we look at compost tea as giving us microbial life only. So there really is no nutrient in there for the grass or the system, and there is no organic matter fraction. So compost tea can be used in the beginning of an agricultural or a turf program, or if compost is used in the beginning, then this can follow in as you phase out the more expensive and labor-intensive top dress application, and this can take its place. The liquid programs that I develop for different clients around the country, if I have the ability to have compost tea, this material becomes the foundation of the liquid program, and I'm using it roughly 1-to-1 with water. So for every gallon of compost tea that goes into the final spray tank, there's a gallon of water. So 50 gallons of tea, 50 gallons of water. We're trying to generally deliver 2 gallons per 1,000 square feet or 100 gallons of finished solution to the acre. So in telling you what it is, my comment on compost tea up front is that we should look at this as a tool that we potentially have to use to make a positive influence on growing the soil biomass. Now that being said, the early on compost tea was certainly has been a valuable product all along, but in its development and in the early years, in the late 1990s, some organic folk that were very anxious in trying to find that silver bullet, that magic wand that makes all things organic, wildly successful, sort of branded compost tea as that material that became the potential savior to build the organic industry as that alternative, to the conventional side of things. And so, for a number of years, compost tea labored under that burden, and it's not that material. If you just take compost tea in and of itself with few other additional resources, you probably will be disappointed in what ends up happening. So if we have a soil system here that may have good resources in the soil, or it may not have good resources in the soil. And then apply compost tea to that. Well, if we apply it to a soil that doesn't have good resources, not a lot of that compost tea is going to grab hold and become beneficial with microbial development. So when we do a compost tea application, what we have now learned is that, yes, it's a tool, it's a valuable tool, but it is just that, one tool amongst several. And now most of the compost tea programs that you see in turf and landscape have an addition of a nitrogen source and a humic acid source and maybe a kelp source and a molasses source, so that when that compost tea goes out there on the turf system, there are resources packaged with it to ensure that it gets into that soil in a way that will have continual resources to keep it moving in the positive direction. The nitrogen that's in there is to directly meet the short-term needs of the grass plant, as well as some stimulation to the biomass. So that's what we would be doing. We'd be making this batch of compost tea and then putting it off into a spray tank, but we'd be adding one of the water-soluble sources of organic nitrogen, and we would be adding the nitrogen specifically for the grass, and then the humic acid or the kelp or the molasses to nourish and sustain the biomass and to give that material the resources. So when we're looking at it in that respect, that's how we're finally now determining that we can use this material to become a hugely effective addition to a natural program. 100 gallons of a high-quality aerobically extracted compost tea contains the same number basically as a pickup truck full of compost. So in 100 gallons, you can get the same biological life as you can in almost 2,000 pounds of compost, which is about 1.5 yards. As I said, it addresses the biomass only. It does not address nutrient in and of itself. So this is that follow-up material to a top dress application. So it's a liquid extract. It can be many different types of machines. This is just one picture. You can do it as small as a 5-gallon bucket and as big as a 1,000-gallon tank. The machines that I have on different projects that I'm working on, generally we're using a 250-gallon machine. This process is such that we put water in the machine, and then inside of this tank is a mesh bag. In that mesh bag is a high-quality, biologically active compost. The end product of the tea, the quality of the tea, is directly related to the quality of the compost that goes in the machine. So if we start with an inferior compost, we're going to start with an inferior tea, and end with an inferior tea. It's one of the problems with university research on the subject is when it was researched in the 10 years ago when it began to be looked at, it was being done by people that were conventionally trained that didn't necessarily have the background in the organic framework and didn't take into account the importance of a really high-quality compost and testing the compost for biological life. And it was the end result, the tea was looked at as more under the guise of fertility. What's it going to do for the system in the short term? And the answer to that is not a whole lot. So when you look at it side by side with a fertilizer application, it doesn't stand up the way a fertilizer does because you can't look at it that way. So this is a process where we put this compost in the machine, turn the machine on, and it basically is gently agitating water. So there's agitating water, and not just really passively gentle, but I mean there's some turbulence to it. And that is separating the microorganisms from the physical compost. So that within 2 or 3 hours with a good machine, all of the living life in that compost can now be extracted into that water solution. What remains in that mesh bag is simply the physical compost or that organic matter fraction. So that's in there. At some point that comes out of the machine and goes back to a compost pile. And now we have these organisms swimming around in this some amount of water. We could choose after 3 hours to take that material out and go out and spray it right away as an extraction. So we had X number of organisms in the compost. We have extracted X number of organisms, and now we're going to take that out and spray that. Or we would have the opportunity to invest about 20 to 24, maybe 36 hours into an additional process called brewing, and then to the tank we would add food sources. They could be things like kelp and humic acid and wheat flour, rice flour, straws, fish fertilizers, molasses, materials that would grow. They're strictly bacterial foods, which would take that X number of organisms that's extracted and then grow that to an extremely large number. At the end of that process, that material is then taken out, cut 50-50 with water, and sprayed on the turf system. So two different ways, some people do it one way, some people do it the other way. Two different processes, all the same in origin. And the bottom line is that we end up having a material that can be, put down at rates as low as 15 to 25 gallons an acre. Right now, that my most recent work has shown that the most effective rate for turf is closer to 50 gallons an acre, or roughly a gallon of concentrate per 1,000 square feet, knowing there's 43,560 square feet to the acre. So we round it up, so 50 gallons to the acre. We understand that it is fully alive, so I make the comment to be gentle. If it comes out under high pressure, right against that wall, everything's going to splat and it'll die and you'll have brown water. One of the most important things, if anybody decides they're going to brew compost tea or make it, is you have to test it. I get involved in the analysis of compost tea and extractions and how good or bad they are. And I just finished one product where it was a large estate property, and they were doing everything in-house, but they had a contractor coming in making the compost tea. And they had never looked at any of the real follow-up to testing, and it basically turned out that they were spending all this money and all this time, and they were simply producing jugs of brown water that had little or no biological life. In fact, they really compounded the problem by thinking that they were being wise in taking pond water as the water source for the tea making, but what was happening was they were taking anaerobic aquatic bacteria and now growing them in this solution just like they could grow an aerobic organism, and the tea was so bad that it was actually reversing some of the good stuff that was already going on in the soil. So again, this is all about science, and there's a right way and a wrong way to do it, and really the only way to determine whether things are on track is to test. Soil testing. So this is the basis for all of our inputs in a program. Rarely do I move in a direction without soil testing. If you are a lawn care company and you have, several hundred or several thousand accounts, are you going to feasibly test every single site? Probably not. Many organic landscape contractors will test and charge for it in the beginning of a program as part of that annual service, so that it, there's a lot of successful natural companies that include soil testing and charge for it. One of the things that we know is, through years of biological testing of soils and turfgrass systems, generally speaking, if we have the same textural types of soil that have been under similar management strategies, and we're growing the same type of plant material, in other words, the same type of grass, we can make some assumptions that biological life is similar across different properties. And I've done firsthand testing where we did 12 athletic fields in one community, separated by several miles, so they weren't, right next to each other, so all over the city. And they had been in a natural program for about 4 or 5 years, but we tested every single one. And I think we spent $5,000 to run full textural, full nutrient, and full biological across the board. And what we ended up finding was the biological results were almost identical across the board when we had the same general soils, same general management program, and the same types of grasses. So we can make some of those assumptions. Most important thing when we're doing program work is the acidity of the soil. So whether we're acid or alkaline or neutral or where we want to be, we know that grasses prefer slightly acid soils. So if we have pHs that are down in the 5s, nothing is going to work properly until we get the pH established into the desired range. So that can be quickly determined with a fairly decent high quality pH meter to determine if we are in an acidic condition. What the nutrient analysis, for residential work, the only test I would generally ever do would be a nutrient analysis, the inexpensive $10, $15, $20 test. If I am doing new construction, homeowner association, condominium development, commercial work, I'm always going to add a textural test to that, because what happens, we all know, it's no secret, I'm sure you've all run into this, that you work on a new site, and what happens when they do new construction, if they go into a virgin site, first thing they do, strip the topsoil. Topsoil gets sold off, generates capital, build whatever is being built, then the gravel and what remains is sort of just leveled out, and usually it's some relatively shallow amount of an inferior topsoil is brought back in to repopulate or replenish the site. Then we come in and try to run an organic program, and we have very difficult time because the soil doesn't have the resources that it should have, and then organic is not going to work. If we have a biologically depleted soil, if it's a gravelly soil, I mean, we got an issue. So what we do is a textural analysis to right up front substantiate, here's what I'm working with. So that is for basically self-protection, that you are not owning problems that were created by somebody else. If you go in and you don't test and you try to do it and manage it for a couple of years and things go the wrong way, well, it's hard after 2 years to say, well, the problem's in the soil. You point that out. That's one of the big difference between an organic program and a conventional program. Synthetic, water-soluble fertilizers will work perfectly in those challenged, gravelly, junky soils. I mean, you can grow, we all know in a sand-based system, you can grow in sand. You can grow with no organic matter as long as the nutrient is soluble and does not require microbial intervention to break down. And in the next few minutes when we talk about the way organic fertilizers work, that's what is absolutely required, is microbial intervention to make that fertilizer be able to work. So if you don't have the resources there, you have to put them there. And the only way you know that they're not there is if you test. So if we're going to do that nutrient test, you're going to do that. What the advantage of the nutrient test does is it points out deficiencies, like that potassium deficiency I mentioned. We don't know whether we're deficient unless we have some type of a test. We can do a quick textural, out in the field. Short of that $75 textural analysis, you can simply go out and take a little bit of soil in your hand and moisten it, and you just work it between your thumb and fingers and try to form it into what's called a cast. A cast is simply a little ball. And if you can roll it into a cast and you can hold that ball as a firm cast, then you have adequate percentages of sand, silt, and clay. The next step to that is to take that soil and work it between your thumb and fingers and what's called ribboning it out, just like, when we were kids and you had modeling clay and you made those little clay worms out of it. You try to do that. And if you can ribbon it out to be about 1 inch and it breaks off, then it's some clay, fair amount of silt in relation to the sand. If you can ribbon it out 1.5 inches or so and get a nice thin ribbon, then that tells you you have adequate amounts of clay with the silt and the sand in generally the right percentages to have what would be a texturally balanced soil. If we were engineering a soil from scratch to be the ideal topsoil to grow turf grass, it would be 65% sand and somewhere between 6 and 8 or 9% clay, and then the balance would be silt. And that would give us all the resources that we want in the right amounts in order to have a soil that would support grass to the best of its ability. Now, do we always have that? No. The part of the country where we find that more naturally is further north, back up in the Northeast. In New England, that is about what the textural capability of the soil is. It's a sandy loam at 65% sand. In different regions of the country, I'm doing a project right now in Cleveland, and it's about 18, 19, 20% clay. So, almost double the amount of clay that you would really like to see there, and sand is way down at 45%. But are we going to add sand to mitigate and change the clay? No, we're going to work with what's there. So it's an understanding of what's there and then how to work with it. So for this nutrient analysis, we're going to take either a soil probe like that or simply a trowel, and going to go down into the 3 to 4 inch range down in the root zone and take multiple samples from the lawn. I'm going to take 7 to 10 different spots and grab little handfuls or little trowelfuls of soil. Going to mix all of those individual samples together to form one composite sample. I usually leave it out overnight on a paper plate or something to air dry a little bit. If it's excessively wet, it may have to stay out longer than that. And then I'm going to clean it. I'm going to remove what I call organic debris. That would be blades of grass, pieces of the thatch layer, pieces of the root zone. Because when they test for organic matter, the test is referred to as LOI, loss on ignition. They weigh the sample, they burn it, and then they reweigh it. All the organics burn off, all the mineral component stays. So then that burned off or that loss of weight is then relayed to us as a percentage of organic matter. So that organic matter is a percentage by weight. When you do this, and then you would pack this up, you're after, for a nutrient analysis, you're after roughly 1 dry cup of soil. So we're going to take a cup of soil, put it in a baggie, and then send it off to the laboratory. This nutrient analysis will give us pH levels. It will give us organic matter. It'll give us a calcium to magnesium ratio. We know that turfgrass science tells us that grass prefers more calcium than magnesium. The biomass, same way, prefers calcium. There's a school of thought that says that high magnesium soils have a greater tendency to compact. High magnesium soils are more conducive to dandelion pressures and certain weeds that thrive on the high magnesium. We get the macronutrients, and then we get micronutrients, and then this cation exchange capacity. When you do a soil test, a nutrient analysis soil test, and you send it to a laboratory, the most important thing is that you want to pick one laboratory and stick to it. So because if you follow up in successive years and you switch or bounce from one lab to another, you could get into problems depending upon that laboratory's protocol. So when that lab receives this sample from you, just like we talked about hydrochloric and sulfuric acid makes treble superphosphate reacted with black rock phosphorus, or the biomass exudes organic acids that solubilize insoluble minerals, they take this soil and they mix it with an acid, and they mix it in water and acid and put it into solution, and that acid solution solubilizes all of those nutrients. There's different types of soil testing protocol, but in generally speaking, there is a strong acid extraction and there is a weak acid extraction. So a laboratory that does strong acid extraction is referred to as Mehlich 3, MEHLICH 3, Roman numeral 3. That is a strong acid extraction, meaning they put a strong acid in there, and all the nutrient that's in that soil is going to be pulled out into a form that can be relayed to you as parts per million or pounds per acre of that nutrient. A weak acid extraction is just the opposite. It's a much weaker acid, and it does not pull all the nutrient that's in that soil into solution. It only pulls part of it into solution. And then that number is relayed to you as ppm or ppA. So many people think that the weak acid extraction is more similar to what's happening out in the natural world. Lot of nutrient in the soil, the vast majority of it insoluble, small percentage of it soluble, small percentage of it readily available to the plant material. But if you end up going from one lab to another, you could get exactly the same soil, 2 different soil tests. Strong acid might give you a number of 3,000 for calcium and 175 for phosphorus, and the weak acid would give you a number of 1,500 for calcium and 25 for phosphorus. It's the same phosphorus, it's the same calcium, it's just 2 methods of extraction. So you pick one lab. There's a laboratory right down here in the region that a lot of people use, a private laboratory, A&L, Eastern Agricultural Laboratories, just down in Richmond. That's a Malic 3, strong acid extraction. I don't think University of Maryland soil tests anymore, but on their website they refer you to other laboratories, and some are strong acid, some are weak acid. They're both legitimate, they're both good, but you just don't bounce back and forth because in successive years you could get drastically different numbers. The textural analysis gives us the percentages of sand, silt, and clay, gives us a key to the soil's ability to hold on to nutrient. In other words, the cation exchange sites that I referred to, those negative sites that are on some of the clays, not all clay, there's different clays, there's mortallite clay, kaolinic clay, but nevertheless, there are negative sites on clays. So by looking at the percentage of clay, we can make some assumption on how well we can hold on to nutrient in that soil. That gives us a key on how we may want to fertilize. If we have a soil that has the ability to hold on to things for a long period of time, we know that we may not necessarily have to fertilize, one way. We can go another way. So we can move from either maximum doses or spoon feeding, depending upon clay and nutrient retention. It gives us a key to the ability of a soil to hold on to water. Gives us a set classification of sandy loam. Loam is another term that's misused in the industry. We tend to say we're going to buy a load of loam to work on a project. We're actually buying a load of topsoil. That topsoil may be a loam, but loam is the textural classification based on the individual percentages of sand, silt, and clay. There's something called the USDA textural triangle. Clay is on one leg of the triangle, sand on here, and silt on here. You take those percentages from the soil test, draw the intersecting lines, and then you get the textural class. Loam is smack dab right in the middle of that triangle. One corner is heavier to sand, one corner is heavier to silt, and one corner heavier to clay. So we could have a loam, a silt loam, a clay loam, or a sandy loam, depending upon, and they all function and act very differently. This also test will give us a tendency on what we might expect for compaction. The third test is a biological assay, an expensive test, as you can see. And this is the real-world snapshot of what is living in that soil. I don't do this for all properties. I do this when I'm involved in a big project. If I'm working with a municipality, if I'm doing sports fields, I might not necessarily do this on every sports field. I might take 3 sports fields that I know the soils are similar, the grasses are similar, and it's been in the same fertilizer, and take some soil from 1, soil from 2, soil from 3, put them all together and run one biological assay. What this test is telling me is the total number of organisms that are extrapolated from this test that are living in that soil system. So the total bacteria, the total fungi, how much is there in total? But most importantly, it gives me the active fraction, because it's active fungi that are giving me disease resistance. It's active bacteria that are breaking down organic fertilizers. So then I look at that active fraction in relation to the total fraction, and then I get strategies on what I need to start to get that soil in the position that I want it to be to support good organic management. So if I had a lot of total bacteria there and not a lot of it was active, I could simply do either a liquid or a dry application of molasses, because molasses as a sugar is a direct bacterial food. So I can wake up, stimulate, and activate molasses within a couple of weeks, bacteria within a couple of weeks just by a molasses application. And we're talking small amounts. 1 ounce of molasses will make a positive effect on 8,000 square feet of turf grass. 1 ounce of molasses costs about 12 cents. So it's a very inexpensive thing as an additive. If I have a good total number of fungal organisms in the soil, but I don't have a lot of that active, then I'm not going to get good disease resistance. I'm not going to get good balance to my soil. Then I can simply make an application of either a liquid or a granular humate product, a humic acid. Humic acid being an extract of humates. So I can simply mix between 2 and 4 ounces of humic acid in a gallon of water, add in 2 gallons of water, put it down to 1,000 square feet, and I can activate dormant fungal life in a very short period of time. So that is what this particular test does for me, is to allow me to begin to develop programs to very specifically address the soil biomass. We know that these organisms that we're talking about will not colonize the root systems of weeds in the same way they will grass, and they will not bring the positive resources to weed populations that they will to grass plants. So that's where the refining of the soil biomass and getting things in the right place. So in lieu of doing this type of a soil test, if I were developing an organic lawn care program that could be all granular, it can be all liquid, or it can be a combination of liquid or granular. So that's where we are now in the world of organics. 10 years ago, you couldn't really do an organic liquid fertilizer program unless you wanted to use a fish fertilizer. And if any of you have ever used it, you're fully aware that if you take a fish fertilizer and spray somebody's yard of 5,000 or 10,000 square feet, it's going to be a lingering odor for a period of time and not generally, acceptable. So we now have odorless organics. So the whole playing field has changed. But what we would do on broad spectrum development of an organic lawn care program is we'd include a granular organic fertilizer. We might even include one of these granular humates. If we have the ability to deliver liquid applications, then we're putting together programs that involve liquid humic acids, liquid kelp. The resources and the materials that are in kelp are the same things that the grass depends upon. The same amino acids, the same types of proteins that we find in kelp are the same ones that stimulate, the grass plant, or that the grass plant produces itself in its own photosynthetic process. So putting together a program that would involve a liquid application of kelp and humic acid and molasses, all preemptively going up front. And none of that is addressing nitrogen. That is all materials that is addressing the biomass. So it's important when we develop an organic lawn care program from the nutritional perspective to always remember that we're developing a two-tier program. So up here, we need to have product input that's going to address the immediate needs of the grass. If we don't, the grass is going to suffer and will never meet expectations. So up here, that's where our nitrogen comes in, up here, addressing the immediate short-term needs of the grass. Down here, we have a different tier of product that is addressing the health and quality of the soil. This is the humic acid, the kelps, the molasses, the microbial inoculations or stimulants. So in the course of a year's program, we're addressing both levels, and if we do that properly, by the time we get to year 3, these two lines are coming together, and now we can rely more heavily on soil inputs and less heavily on the nitrogen for the grass. because the soil is picking up the load for some of the nutrition for the grass. Soil test is all about interpretation. So we're looking at relationships between things. So we look for deficiencies, of course, when something is below optimum or low. But we know that there's a relationship between pH and the availability of nitrogen, phosphorus, potassium, calcium, and magnesium. If pH is extremely low or acid, that stuff can be there but not readily available. There's a relationship between organic matter and available nitrogen. Relationship between calcium and magnesium. So we begin to look at this and simply try to get this into balance. All just pictures that aren't with the lights for television here, not going to show up great, but all pictures of turf systems that were guided through transition based on appropriate soil testing. Municipal playing field, no weeds, little touch of clover here. This clover was here for 75 years. It was part of this system. When we started the organic program here, it was about 30% broadleaf weed pressure. So the organic program reversed the weed pressure. The broadleaf weed is all out of there. Clover, because clover is a stoloniferous grower, and this is a northern system. These grasses are either tillering or rhizomatous grasses. Clover is perfectly compatible with the way the grass plant grows. So they become natural, they naturally can grow together very well. So this little bit of clover was never determined to be something that we needed to eradicate. Residential, brand new, $1 million landscape in a $10 million house. And the contractor paid no attention to soil, quality of soil. He worked soil in cold, freezing weather late in the fall when it was soaking wet and ruined soil structure and got into problems. 50% of all the plant material here was dead within a year. This homeowner has put probably $350,000 into replacement of this landscape. They brought me in as a consultant to try to salvage what could be salvaged, and we went from there. This was vegetables grown in 82% sand. This is almost hydroponic culture. The idea, again, that soil testing determined what we had, and we developed an organic program. Horse pasture that we carved out of the woods in New Hampshire. And this is a situation where we were allowed to spend the money to engineer soils. So it was engineered at 65% sand and 7.5% organic matter. Today, this pasture is growing on less than 1/2 pound of applied nitrogen a year. We just give it a little touch of fertilizer in September. It's all being done biologically because the resources were allowed to be put there in the beginning to make this, happen. So this is a project that gets compost tea and just a touch of nitrogen, a little bit of kelp, a little bit of humic acid. So, when you are managing pasture for horses, these are quarter horses, 1,200-pound animals. You're supposed to have 2 acres of pasture for every animal. So 3 animals, we should have 6 acres. We're supporting 3 animals on 1 acre, and the other ½ acre has 4 miniature donkeys, and we never go without a blade of grass all during the growing season. And again, minimal fertilizer because it's all happening in the biomass. We hydroseeded it, grew it out. There's our first liquid compost tea, and this is what it grew out to be, all through 2011 and still being managed. And then this one here, this is a high-profile client in the movie business. Couldn't keep grass on their pasture, but it had always been done with synthetics. We came in and did the appropriate testing, made the recommendations, changed a few things, aerated the soil, loosened it all up, and it took about a year to turn it into that. And then that. So the idea that we can come through and make these kinds of changes all governed and dealt with by soil testing. So if we have an acid soil, we adjust it with lime initially to get it into the right spot. Once we get it there, the organic program will hold it there. So the idea that lime has to happen, and of course pH varies in all regions of the country. It varies within, regions right here in the mid-Atlantic. Calcium to magnesium ratio determines the choice of lime that we use. Dolomitic lime is the traditional lime that's high in magnesium, and calcitic lime is high in calcium. Most soil tests now indicate calcium as the lime of choice, so that's what we're actually doing. We're applying it in the fall, but it can be done in the spring. 50 pounds of lime per 1,000 is the maximum rate. It is a slow process that takes 100 days to break down. I was just working this past fall on a turf system of 5.5. It was actually on that Kentucky Bluegrass installation project, and I wanted to, I knew that I needed, if I was going to reduce nitrogen to grow that bluegrass and rely on the biomass, I had to give the biomass the right conditions. And a bacterial biomass does not like a pH of 5.5. A fungal biomass loves the pH of 5.5. I needed to get bacterial dominance. So I came through with a powdered calcium carbonate and made a liquid solution and sprayed that liming material on there, and I changed the pH in 3 weeks from 5.5 to 6.6. All that did for me, I wasn't after a fast liming for the long term, but I needed to get my pH up so I could support the bacterial growth that I needed to have to make the organic work. And that elevation allowed that to happen. I'm not necessarily expecting that to hold next spring, but I do know that once I establish the bacterial biomass to be strong, because those organisms are pH neutral at 7.0, then they're going to keep it that way. And the proof is in soil testing, where we took athletic fields and transitioned them from, and initially they were at pHs that were in the low to mid 5s. And once we transitioned and got through transition and got the bacterial population where we wanted it to be, 6-7 years later, soil tests were run, and every single acre of those athletic fields was between 6.6 and 6.9, and it never changes. It just stays there, because that's what's called the natural buffering process, where the biomass has buffered fluctuations in the pH. Nutrition. So we're going to talk a little bit about the fundamentals and the differences in nutrition. And a lot of it right now is a concept that we're going to change our expectations on what we see as a result of fertilizer. So we know what happens when we use a synthetic water-soluble fertilizer. You get pretty fast green up. So green up can happen in the short term. With organic fertilizers, that is not necessarily the case, because of the bacterial influence needed to process the fertilizer. So in other words, we can get a synthetic fertilizer to work in 48 hours in cold soil. Organic fertilizer is going to be 2 weeks in a cold soil. Once we get to the 2-week period, everything is equal. So now our expectations in the short term change a little bit, especially early in the season. So that's when you get into the real understanding of organics and the science and how they work. So conventional nitrogen can be generally the water solubles. Nitrogen is from urea. There are ammonium, which is an ammonium source. There are nitrate sources. It's synthetic, it's inorganic, it's water soluble, fast release, rapid uptake. There are ways that we can encapsulate that fertilizer with either sulfur or polymer coatings, and there is also science where we can secondarily react that with other materials to create a slow-release fertilizer, and those slow-release synthetics require microbial intervention to break them down. So not all synthetic fertilizer is water-soluble. There certainly is a lot of it that is slow-release, that requires the biomass, but the difference is, even though they require the biomass to break them down, those materials in and of themselves, because they don't have an organic matter component to them, don't do much to build the biomass, to push that biomass to the next level. They can facilitate and use the biomass to get to the grass plant, but they don't help in the overall growth of the biomass per se. If we are using the soluble fertilizer, so if we're using the 4-step program, it's a series of 4 or 5 applications of a soluble material. It leaves the soil quickly. It gets in quickly, and it leaves rapidly. And cost increases. If we have those typical water-soluble fertilizers that have their origins in what's called the Haber-Bosch process, and the Haber-Bosch process is that process that produces urea, where they take anhydrous ammonia, which is 72% nitrogen, and they react it at 350 degrees and high 3,000 pounds PSI pressure, high temperature, interact that ammonia with carbon dioxide, and the end result is this urea product. Urea is the 4600 soluble nitrogen source. In that Haber-Bosch process that involves petroleum and natural gas, so petrochemical input, there's 5 tons of petrochemical input to produce 1 ton of the fertilizer. So it's a huge petroleum, input into that material for its production. So in conventional agriculture, I think it's determined now that conventional agriculture accounts for between 17 and 19% of all the petroleum that's used in the United States. And a big chunk of that is used in the production of fertilizers that fertilize conventional ag fields. So big petroleum influence in that material. Natural fertilizers, the nitrogen is from plant or animal source. All the nutrients are from plant, animal, or mineral. It is generally water-insoluble nitrogen. It is slow release. It requires microbial breakdown. That newer amino acid product I told you does not require microbial breakdown because we are giving the plant amino acids, the same amino acids that it would be producing itself in photosynthesis. So therefore, that type of a product will work organically in cold soils. So, and it works quickly. It works in 72 hours, and it can work in cold soils. So that is now becoming the answer to that early season green up, if that's something where, we have an issue. Green up of grass, we have to acknowledge that it's more to do with soil temperature than it is applied nitrogen. Soil temperature greens up. Nobody fertilizes up and down the highway, and it all turns green every spring. But as a population, we are impatient. We want everything yesterday. So in the springtime, if you're the first one in the block to have the brightest green lawn, that's the measure of success. So, we understand that there's a difference between organic. This newer amino acid formulation allows us to be somewhat closer to the use of synthetics in our anticipation of what we would see as green up. Sustained benefit. This material has longer-term benefit to build the system. More measured growth and cost-effective because very little petroleum is used in its production. We have to understand that plants can only use inorganic nitrogen. So a grass plant can make absolutely no use of organic nitrogen. So if we have an organic form of nitrogen from an animal byproduct or a grain, the grass plant cannot use that. The 2 inorganic forms that the plant can use are ammonium, NH4+, and nitrate, NO3-. Those are the 2 inorganic forms that are found in the soils naturally. So we identified them and 75 years ago went to a laboratory and created the synthetic version of that fertilizer. So those are the ammonium and the nitrate synthetic soils, so what we call synthetic organics. So that is what was created because it would work seamlessly. It would work very rapidly in the soil. You take it out of the bag, you put it down. When it comes in contact with moisture, bang. It's right there. It's already in the form that the plant can use. That's where you get that fast reaction. Natural fertilizers work more slowly, again, because we have this organic form of nitrogen that has to be able to get there into that inorganic form. So if we have that organic N that's water insoluble from grain or an animal byproduct and we put it down on the soil, we're looking at an 8 to 10 day period before the grass is going to get the benefit of that, because those bacterial organisms are now going to interact with this. The process, the science of it is mineralization. So we have mineralization where bacterial microbes mineralize that organic nitrogen. They break it down, they get it in their bodies. They are the vehicle that serves to convert to the inorganic form. The first step in mineralization is the conversion by bacteria to ammonium. Ammonium being one of the two inorganic forms, and that is readily available to the grass plant. We have these cation exchange sites over here that have these negative charges. Ammonium is a plus charge. So these sites grab right onto some of that, and they hold ammonium there. We call that reserve nitrogen. Now we have another trophic level of bacteria coming in called nitrifiers. Nitrifying bacteria pick up some of this ammonium from this first conversion, and they secondarily convert it to nitrate. Nitrate is a negative charge. It's repelled by the cation exchange sites. It is water soluble, and it goes right into the grass plant. Not water soluble to the point where it's released all at once and can cause a problem to the waterways. Like a synthetic nitrate-based fertilizer is all soluble, and you put it down, and it just is there, and if it doesn't get sucked up by the grass, it goes somewhere else. That doesn't happen in organic. So that's the vehicle, mineralization, that takes it from the organic form of nitrogen to the inorganic form of nitrogen. When we evaluate what we need to grow grass, we look at nutrient levels, availability, the pH, interactions, and environmental conditions. Grass gets nutrients it needs from minerals, organic matter, the atmosphere to a much lesser extent, and some of it through gas exchange, some of it if there's clover in a system, but from fertilizer. So grass will not die from lack of fertilizer. You can take grass and never fertilize it, and the grass plant won't die. We have grasses like the hybrid Bermudas and the Kentucky bluegrasses that have a genetic need for higher levels of nitrogen than other grasses. Kentucky bluegrass has a much higher genetic requirement for nitrogen than a tall fescue. Tall fescue can get by on minimal nitrogen. You cannot fertilize a fine or a tall fescue lawn, and it will not die. Why we fertilize grass is because when we are trying to manage grass to a higher level of expectations, grass as a horticultural crop needs more nitrogen than nature can provide on its own. So that's where fertilization comes in. If we have really low expectations, then we can get by with little or no fertilizer. If you put down Kentucky bluegrass lawn or a hybrid Bermuda that has a lot of need for nitrogen and you don't fertilize it, you're going to find it go right down. In cool season regions of the country, you can put down a grass seed that's 1/3 fescue, 1/3 perennial ryegrass, 1/3 Kentucky bluegrass. And if you fertilize the dickens out of it, the bluegrass is going to overpower and choke out, and everything will be gone, and the bluegrass will survive. If you back way down on fertilizer and give it very little, the bluegrass is going to give up the ghost, and the fescue is going to predominate and be very happy. So that's the relationship. So the bottom line is we fertilize grass when we're trying to meet expectations. I mentioned early on that there's a direct line between proper nitrogen levels for high expectations and minimal weed pressures. So if we fertilize along those lines, and I'm not talking excessive fertilizer, I'm still talking at the highest level of fertilizer will still be well under the Maryland state law of 3.2 pounds of applied nitrogen a year. We're under that. But the idea that if we're at 3 pounds or if we're at 1 pound, we're going to suppress more weed pressures at 3 pounds than we will 1 pound. So that's where fertilization comes in with grass. These are the nutrients that are in a fertilizer bag. Nitrate nitrogen, an ammonium nitrogen, or not in the bag, but these are the nutrients that the grass requires for its growth. The two forms of inorganic nitrogen, potassium, and that K plus is in the ionic form. That's the form that's expressed, that's attracted to those cation exchange sites, and then phosphorus as H2PO4 as phosphate. So that's what the plant actually needs to grow on. When we look at a fertilizer bag, we have 3 numbers on that bag called the analysis. And then within that analysis, there is a ratio of one number to another. Different types of turf, different types of applications involve different ratios. But in the potassium and the phosphorus, potassium, K plus is potassium in the ionic form that the grass can use. Potassium, as it's expressed on the bag, is expressed as potash on the bag. Potash is only 83% potassium. So if you have a number on the bag for potassium, a potash of 4, only 83% of that is actual potassium. Phosphorus on the bag is expressed as phosphate. Phosphate is only 42% phosphorus. So if you have a 2 on the bag for phosphorus, you know that there's only 42% phosphate in that bag for the analysis. So that's a little bit difference between how potash and phosphates between phosphorus and potassium. Big concept. This is really the heart of what makes organic fertility work. There is nothing in that bag of fertilizer that remotely resembles plant food. There is absolutely no plant food in a bag of lawn fertilizer, whether it's synthetic, whether it's organic. Doesn't matter. There's no food for the plant in that bag. What is in those bags are simply raw materials, nitrogen, phosphorus, and potassium. Those raw materials, those mineral nutrients, do certain things within the physiology of the grass plant. So if we just focus on nitrogen, because nitrogen is used by the grass plant in the largest amount, when we make an application of fertilizer containing nitrogen to the grass, we do this. We stimulate top growth. We stimulate some root growth. We stimulate horizontal extension, the reproduction of the grass plant. In my mind, this is one of the most important respect. I could care less about what happens up here. Why should we focus on blade growth? Blade growth means nothing unless we're trying to recycle a lot of grass clippings to the lawn or come up with material for a compost pile. Because blade is going to be cut off. That growth is the most important stimulus from nitrogen because that's thickening the turf. And that's what's going to keep out the weeds. So if I'm handcuffed and I can't use an herbicide, I've got to come up with every strategy I can to make that grass so dense that the weed can't get in there. That's how I'm going to do it. I'm going to stimulate horizontal extension. Another thing that fertilizer containing nitrogen does is it makes the grass get greener. Green, as we know, is chlorophyll. So as it greens up, chlorophyll density is increasing. So now we have that blade of grass that has chlorophyll. It reacts with energy from the sun in the presence of carbon dioxide and moisture. Just like that clover plant, on the underside of that blade of grass are those microscopic openings called stomates or stomata. Open and close at dawn and dusk, generally when the air is the calmest. The carbon dioxide and moisture enter right into the grass plant. Chemical reaction happens with the chlorophyll, and carbohydrates, sugars, and amino acids are produced. And that's the plant food. That's what the grass plant grows on. It grows on carbohydrates, amino acids, proteins. That is the plant food. It's not the fertilizer that's the plant food. It's the byproduct of photosynthesis. So now that grass grows, its short-term growth is happening with these materials. At the crown of the grass plant, which is an area right above the soil, we have a huge storage capacity there to store carbohydrates and amino acids for those times of the year, which are summertime, when we generally have low carbohydrate production. And then a balance of those carbohydrates become exudates that go right down to the root system that nourish the microbes, particularly the mycorrhizal fungi, that are now colonizing the root system. So we use those exudates to draw beneficial organisms to the roots of the grass plant. So now photosynthesis becomes the real key in how fertility is happening and how nutrition and food actually becomes available to the grass plant. So now when we talk about some of these new micronized soy powder products that are amino acid, and we introduce them to the system, we are now giving the grass plant the same amino acids that is producing itself in photosynthesis. So we are literally giving a food source across the board. Nutrients have to be available. We've talked about that. They have to be soluble to be taken up by the root. Management, environment determines whether they leach, volatilize, or used in some cases. You know, if you have a depleted biomass, organisms can use up all the benefits of the fertilizer before the grass can even get it. So we have to understand that. With the conventional water-soluble fertilizers, a reaction looks something like this, taken right from an extension website. Growth rate increases sharply 2 days after application. Peak growth rate is 7 to 10 days after application, and it tapers off to the original growth rate 4 to 6 weeks after application, creating a peak and a valley of fertilization. So at 7 to 10 days, soluble nitrogen has been released more rapidly than the grass can process it. So what can end up happening, and we've all seen it, that if we do a synthetic application and temperature spikes up really warm, you get a quick flush of relatively weak, lightish green growth because the grass is trying to process all of that available nitrogen. So now you have basically more than you need, and now at the end of 4 to 6 weeks, it's gone and it's not there. When we talk about grass, we talk about the key to growing grass is about reducing and eliminating stress. Excess available nitrogen is a stress. Deficient nitrogen is a stress. So now if we're fertilizing at 4 or 5 pounds of nitrogen, 1,000 square feet, which you can't do here in Maryland anymore, but in that old school mentality, stress, 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 you've got a whole bunch of stress events that you're packing on to each other, and it's not really leveling it out. Where an organic, if we call that a synthetic fertility curve, an organic fertility curve is more like a straight line. You give the grass what it needs when it needs it, and it's being delivered over time as opposed to excess. One of the problems in that 7 to 10 day period with the synthetics is that if you have a sports field that has a bare goal mouth, or if you have bare at the center of the field, or if you have a lawn that has a lot of weeds, or if you have a lawn that has bare spots, you don't have turf grass roots sucking up that nitrogen. And then the fate of that nitrogen is not ending up into the grass plant. That's the concern with the Chesapeake, is that now we have some nitrogen that is finding its way elsewhere other than being taken in by the grass plant. So these peaks and valleys have a detrimental overall effect on the grass because short periods of growth followed by short bursts of rapid growth followed by periods of slow deplete carbohydrate reserves, reduce root, eventually thin the turf system out. So we know that cool season turf grasses thrive at soil temperatures of 55 to 65 and air 65 to 75, and warm season grasses higher, 65 to 75 soil and 75 to 90 air. So if we're here in Maryland and we're growing a tall fescue and it's the middle of the summer and it's 90 degrees, that fescue is not photosynthesizing. The Bermuda would be, but the fescue is not because it does not have the genetic ability to photosynthesize in hot weather. Cool season grasses are referred to as C3 grasses. Warm season grasses are referred to as C4 grasses. And there's a lot of physiological differences, and there's the differences between the two grass and functional and application differences, but bottom line is C3 means the cool season grasses begin the process of photosynthesis with a 3-carbon compound. C4 means warm season grasses begin the process of photosynthesis with a 4-carbon compound. So that means that Bermuda here in Maryland is very efficient at photosynthesizing and producing its own food resources at warm summer temperatures. But that fescue that may be grown here is extremely inefficient because it simply does not possess the genetic capability to photosynthesize and process carbohydrates at warm temperatures. So that's where we end up, understanding that. So the idea that if we're, doing that synthetic where you're getting this quick burst of growth followed by slowing down, and then through the summertime, ultimately that can have a detrimental effect on the cool season grass. We're always matching nitrogen input to the growth pattern of the grasses. If it's a cool season grass, no high nitrogen early spring or summer, moderating the peaks and valleys, looking to build up the reserve. That high, I still say that it takes 5 pounds of nitrogen, 1,000 square feet, from all sources to grow high quality grass. But I don't have to get that all from fertilizer. So that's the big difference. Yes, if I want high quality, I don't care whether I'm growing Bermuda, I don't care whether I'm growing bluegrass, or trying to maintain a high quality, any other type of turf grass system, I'm going to be looking at roughly 5 pounds of nitrogen, 1,000 square feet to do that. But if I'm recycling grass clippings, I'm going to take a credit, I'm going to set my nutrient budget at 5 pounds. I'm not going to ever get more than 3 or 3.2 pounds from fertilizer. I'm going to get my other from either something like recycling grass clippings, which I'm going to chalk up nitrogen to my budget, or I could do a microbial inoculation, and it could be a compost tea. It could be one of the, like the product that we talked about, the microbes, those kinds of things. They're non-nitrogenous in nature, but because they stimulate the biomass in such a way that they facilitate within that biomass a greater production of internal nitrogen happening. So I'm going to take a non-nitrogenous microbial input, but I can chalk up a 1/2 pound of actual nitrogen from it, because that is going to ramp up that biomass to produce more on its own, and I'm going to take advantage of that towards my credit that I take to do it. So that's why when I come up with my laundry list of inputs into a system, that laundry list will include some nitrogen sources. Kelp is not a nitrogen source. Molasses is not a nitrogen source. Humic acid has a really minuscule, it can be as like 1/10 of a pound of nitrogen in some humic acid formulations. But those 3 materials really have no direct nitrogen in them, but they combine in such a way with other low-dose nitrogen input sources that sort of the cumulative effect is greater than the individual components. And that's really where organic is moving. If we're looking at that bag of granular organic fertilizer, these numbers, generally for the first number on the bag, give us a quick indication on what type of fertilizer it might be. It's not a hard and fast rule, and we certainly can have synthetics down in the 14 to 18% range, and we certainly can still have transitional products or the bridge products up in the higher range. But as a general guideline, that's what we're looking at, with bridge product or transitional product being defined as a material that contains some natural organic combined with some either synthetic form of nitrogen or a biosolid sludge type product to get nitrogen. But it's a combination of some natural organic and then some synthetic or biosolid. Traditional, non-traditional sources, compost top dress. If we choose to top dress a turf grass system at 1/4 of an inch depth, we know that we're going to get at least, conservatively speaking, at least 3/4 of a pound of nitrogen, 1,000 square feet out of it. And that would be very conservative. With a higher nutritional compost, we're going to get even more than that. So we got that compost tea, non-nitrogenous, but it's going to stimulate the biomass. It's going to put more bacteria there, more protozoans there to sort of ramp up that system. Those liquid fertilizers, and they can be either that soybean material, or it can be some of the fish products, like the fish. We don't really use fish emulsion anymore. Fish emulsion is a heat process where they take all the remnants of the fish and they boil it all up grind it into a slurry. You'd be hard pressed to use that on a residential client. You'd get run right off the property. I mean, in the early years of organic, did one where we did a fish hydrolysate on a sports field. And this actually was a catfish product that was blended with a pennyroyal mint, and so it didn't really have a noxious smell. But I was a manager of a sort of a trial site where it was an adopt a field project, and different organic practitioners said, I'll do that field, I'll do that field, I'll do that field, and they did it at their own cost. And one of them came in with compost tea and fish emulsion, And oh boy, the stink didn't leave that field for about 3 days. I mean, it was prohibitive. You know, so that, yes, it's a great fertilizer if you're doing organic gardening. You know, when I had, you know, in my greenhouse range years ago, I gave up pesticides and synthetics, and I actually had part of the greenhouse range USDA certified organic. And I used fish emulsion. But I liked it because when people walked in there, they knew it was organic. They could tell the minute they opened the door and walked in, oh, this is legitimately organic. So for that purpose, it was good because it got the message out there. But believe me, out in the real world, that's not a material. The newer fish hydrolysates, I just had an email last Saturday, I think, from a company that is now processing different types of, what was he processing? He used to process catfish, and now he's processing squid. So after they take the squid and they cut it all up and they get all that calamari out of it, all the byproducts are now being processed into an organic fertilizer. He offered to, you know, send me some as a trial. First thing I'll do is unscrew and take a sniff, and I'll tell him right now whether it's going to be able to be worked or not. There's a big difference in doing an organic vegetable garden and watering it in with an organic fish fertilizer and trying to think that you're going to spray this, you know, fish product out over 5,000 or 10,000 square feet. That realistically is not going to happen. Returning clippings, microbial inoculants. So we're taking all of these sources of nitrogen into account. Traditionally, we've looked at a grass system's response to nitrogen by the growth rate and the color. How green did we get it? And then how fast did it grow? So we'd take a fertilizer and we'd put it down, and then at 7, 14, 21, 28 days, we'd cut the grass, weigh the clippings, and the fertilizer that produced the greatest clippings over 4 cutting cycles was determined to be the most effective fertilizer. You know, in a lot of our minds now, that's kind of a flawed concept because, again, why should we be concerned on producing lots of clippings when there's other things that may be, you know, more important? I went out to, I have friends, I know everybody at University of Massachusetts Cooperative Extension in turf grass, and we're all friends, and I go out usually once a year and sit through a workshop, and we talk and we chat about the you know, the sort of the state of and the future of the industry. And, you know, things are changing. You know, the turf agronomist out there, he started off 2 years ago his presentation with a jigsaw puzzle. And he had all the pieces of the jigsaw puzzle put together. And it had fertility and cultural practices and irrigation and grass seed. And there was one piece of the puzzle that wasn't put in. And it said pesticides. And he said, that's the piece we're trying not to put in the puzzle anymore. Now, this is from a guy that, this was, I mean, he's a conventional guy. But that's where the thought process is going. Last year, he talked about the genetics of turfgrass and applications for turfgrass and the most important criteria for breeding work in turfgrass for the future. And he listed all the criteria of high-quality turfgrass. And it was like growth ability and slowing down the growth and reproductive capability and insect resistance and disease resistance and lower fertility requirements and color. And he asked the audience what was the most important characteristic up there. And there was an old-timer there, my age, and he raised his hand and he said, I've been in the landscape business for 40 years, and the absolute most important criteria there is color. My customers have to have dark green color, and if I don't have dark green color, it's no good. And this professor, who's not, I mean, he's in his mid-50s, so he's not a kid, walked right up to the blackboard and put a big X through color. Said, get over it. Grass is green. It will get as green as its genetic capability would allow it under a proper fertility program. But far more important is continually being hung up on. I mean, we all remember going through the Midnight Kentucky Bluegrasses and the Bermudas, the Tifton hybrids, and all the color work that went into breeding in the last 20-odd years. And now you know, the idea that we look at these under a new set of eyes, and now we're more interested in the benchmarks that we're looking at is root growth, carbohydrate reserve, shoot density, stress tolerance, disease resistant, things that will reduce inputs and still maintain the same high-quality turf system. So high-quality turf with less nitrogen, with less insect problems. We already now have some grasses that contain natural fungal, symbiotic fungal relationships that give us disease resistance, and your fescues down here are those primary grasses. They contain natural endophytes. An endophyte is a beneficial fungus that is a symbiotic relationship with the fescue plant. It lives right in the seed. The fescue gives some of its carbohydrates that it produced in photosynthesis to the fungus for its survival. The fungus gives alkaloids and chemicals that make it resistant to surface grazing insects, not root feeders, not grubs, but the chewing insects that feed at the surface. Some degree of fungal resistance, some more sort of measured growth capability, all done through natural infection plus enhanced breeding. So we have those capabilities, characteristics that we're looking at, but these characteristics are harder to measure, of course, than just weighing bags of clippings, but clearly these are ones that provide some strong benefit to us. Mycorrhizal fungi, talked about those. Other amendments, when we look at those humates, we talked about those, and it can be done at low rates. 5 to 10 pounds, 1,000 square feet for granular, anywhere from 2 to 8 ounces, 1,000 square feet for a liquid. There are maximum, allocations of humates that you can give to an acre of turf in a year, so you don't go overboard. You can't just go willy-nilly and put this stuff out there. You know that you have a maximum load that you can put out there, in the course of a year. So the successful management of fertility is to deliver enough nitrogen, this is for cool season, enough nitrogen in the spring to get optimum shoot growth without excess at the expense of the root. Because the bottom line is grass will not grow aggressively in two directions at the same time. Cool season grasses do not possess that ability. Neither do warm season grasses for that matter. The difference between cool season grass and warm season grass, cool season in the spring, you get that. And in the fall, you get that. Warm season grasses, and so in the spring, you have a spring growing season and a fall growing season. Period of time in July and August when nothing is happening either way. Warm season grasses, the hotter it gets, the more carbohydrates it can produce in photosynthesis. So when you get to the hottest time of the year, you're getting the biggest activity, and it's slow to start, and then it tapers off at the end of the season. So they're exactly the opposite, and it's all temperature and genetics and what the plant can understand. So where if we fertilize heavy in the spring with cool season grass, you're going to get lots of that, and you're not going to get a lot of root. And you're not going to get a lot of root anyway because the plant doesn't have genetics to do that. One of the things that we don't always take into consideration when we're using pre-emergence crabgrass control products, when we understand the science and the chemistry behind the way pre-emergence work, they don't kill the crabgrass seed, they kill the germinated seedling. So they put down a chemical barrier. When a seed germinates, whether it is a good grass seed or whether it is a weed seed, that seed germinates when three things come together: light, temperature, and moisture in the right amounts at the right time of the year. And that seed sends out a primary root system that lasts for 10 days or so. That primary root system dies back, and a secondary and permanent root system then takes over. Pre-emergent crabgrass controls attack that primary root system and kill it. So that crabgrass seed dies as a germinated seedling. What we don't always take into account is that pre-emergent control also restricts the regrowth in the springtime of the existing lawn. So when we have roots that have sloughed off during the cooler temperatures of winter and are now soil's getting warmer and those roots are starting to regrow, understanding that the genetics of the cool season grasses of the fescues are such that most of the growth wants to happen here, less of it wants to happen here. Now you throw the pre-emergent in, even less can happen down here. So now when you come into June or July and it gets excessively hot, you can have a fescue plant with a relatively shallow root system, where most of the fescue's roots that drive down are grown in September, October, and November down here. Cultural practices. Managing is about reducing and eliminating stress, as I mentioned. I'm just going to introduce this subject, then we're going to get up and take a break for 15 minutes. Stress can happen three ways: environmental, mechanical, and pests. So if we get a pest in the system, that's a stressor. Environmental, as turf managers, we can't do anything about. All we can do is react to it. So we are educated, we understand the genetics of the grass we're trying to grow. We are observant of environmental conditions, and we react accordingly. Mechanical is foot traffic, mowing, tractor tires, other equipment. So we can be aerating a lawn or a sports field, and we're also compacting it at the same time. The trend in the industry is to much bigger lawnmowers, heavier lawnmowers, and those lawnmowers are compacting the soil. I have pictures of a property where it was a relatively small property and probably should have been using a 22-inch trim mower on there, but was using a big ride-on lawnmower, couldn't vary the mowing pattern. So week after week, back and forth, back and forth, back and forth. We know what happened. By the 1st of August, you had a nice strip of grass and a beautiful strip of crabgrass. Nice strip of grass, beautiful strip of crabgrass. So the landscape contractor was causing just the weight, compacting it. So, you know, we understand that when we're doing that, then we take these steps. And, you know, the lawn had no crabgrass, but it was just that the grass went into significant decline. So we're going to touch on mowing, irrigation, aeration, and overseeding. So it's 2 o'clock now, so why don't we get up? I think we have 15 minutes scheduled for a break, and we'll start back up again at 2:15.